Hello, this is the video for MSE 514 presented August 26th, 2016. I've kind of got good news and bad news. The bad news first is that I was looking at problems to solve for today's lecture, and I realized that in order for me to go through a lot of these problems, I really need to give you more lecture content. So even though I had intended to use this video series as a means to focus on solved problems, and in particular solved problems that would be guiding you toward Monday's quiz, we're going to have to put some content in before. So this video is to a large extent going to focus on new content. So that's the bad news. The good news is that we still have a quiz on Monday, and because a lot of this video is going to be focusing on content, there's going to be fewer solved problems, which means that as you prepare for the quiz on Monday, you're going to have a much better idea of what to prepare for. So there's a silver lining in everything. I guess that I had underestimated the amount of content we needed in order to be able to solve these problems, and really we do need to go through the last few sections of chapter 2 before we can work on this. So to remind you where we left off on Wednesday, we left off Wednesday having written out the first law of thermodynamics, right, which is basically that du equals q minus w, which is saying that the change in internal energy is equal to the heat that flows in minus the work that flows out or is done by the system on the surroundings. And then we started talking about holding the work to zero, so having a workless system, and in particular, for our example, we're talking about single component ideal gases, and we defined a quantity here, dq is equal to du by dt v. dt v. So this is the heat flowing into the system when the volume and pressure are both held constant. And after we defined that, we went on to talk about the case where pressure is held constant, and in that case, that allowed us to derive our enthalpy. So we have an expression for enthalpy, which is also a state function, and we had, remember, H is equal to U plus PV, and then remember, this is just for our particular example. In real world material science problems, we're focusing on many types of work, including stress, strain, electric field, displacement, so on and so forth. But in this case, we have a pressure volume work, and we defined QP is equal to delta H. I should probably point out here that this here we'd had a dq v is equal to du. So in the case of a constant volume, we had a du term. In the case of constant pressure, we have a delta H. And that's where we ended lecture on Wednesday. So next, I'd like to talk about heat capacity. So heat capacity is really an expression for the amount of heat that's stored per change in temperature. Right? So if you want to think about it as it's the amount of thermal energy that gets stored per degree C, a degree Kelvin, that the material changes temperature, and that means that we're relating Q and T. And because we just gone through Q, you know that Q can be expressed in terms of constant volume or constant pressure, and that gives us two expressions for heat capacity. We have CV, constant volume heat capacity, is equal to dQ dt V, which is du dt V, and that's because we have this expression du is equal to CV dt, or maybe I should say it's a consequence of this constant volume heat capacity expression. And then we can also write a constant pressure heat capacity, Cp is equal to dQ by dt P is equal to dH dt P. And a consequence of this is that dH is equal to Cp dt. So U and H are both energy units, so say joule, and T is temperature, so heat capacities are energy, or joule per K. Temperature unit. So I'd like to comment briefly here on the idea of a pressure volume and work in general. We talk about things such as pressure volume work, or electric field displacement work, or stress strain work, and you kind of notice a pattern here where we have turn that around. Pressure volume, where we have one term in our work which is really a force, and one which is a motion. And this comes about because we have work, which is energy, and we know that energy is equal to force times displacement. Right? I mean, this is when you have your undergrad physics class and you have little blocks on the table, and you push these blocks with some force, or pull the blocks with some force, and you know how far you pull them. That tells you how much energy went into that. And as a consequence, whenever we talk about work terms, we usually have one which is a force term. This is, electric field or magnetic field, pressure, stress, and then another one which has to do with some type of motion, a change in the volume, a change in dipole displacement, a change in strain. And a kind of a neat extension of that, and you'll see this later, is that you can think about your entropy term in terms of that as well. So when we get to chapter 3 and we start talking about entropy, we're going to have a T ds plus S delta T, and this is going to be a force and a conjugate volume pair as well. And in that case, you can think of your temperature as being a force, and you can think of your entropy as actually being some type of displacement. And in this case, I guess it's a displacement in disorder of sorts. But it's a handy way to think about things and think about these type of pairing. So we talked about heat capacity. And with heat capacity, we said it had units of energy per temperature, and we have some little c, some big C, capital C, 0. But it's also convenient to work with terms that are molar. And in your textbook, they use a capital C to denote heat capacity, and they use a lowercase c, so C sub V or C sub P, to denote molar heat capacity. So that is energy per temperature mole. So how much material is present. Because when I write on the board or when I write in my notes, it's kind of hard for you to tell the big and the little. The notation that I'm going to use is I'm going to draw a line through my C to mean molar quantity. And that's just kind of my personal notation. I haven't seen that in a textbook at all, because textbooks can use capital and lowercase a little more effective than I can. So now within heat capacities, we can have a molar heat capacity. P is equal to Cp, and Cv is equal to Cv. So we can have a molar pressure constant heat capacity and a volume constant molar heat capacity. And we have these, and there is a difference. What is the difference? And we can just take the difference and see that. So we can look at Cp minus Cv. Now your textbook goes through it's about a 5-step proof. It's actually really simple. I'm going to skip that, and I'm going to jump to the consequence of that, or the result of that. And the result of their derivation is that up here, Cp minus Cv is equal to dV by dt constant pressure P plus du by dt, du by dV constant temperature. And that was the conclusion of the proof in the textbook. But there's kind of one more step here, and this is for a real gas. In the case of an ideal gas, the particles are non-interacting, or molecules are non-interacting. And by non-interacting, I mean that we have these two particles, or many of them, and they don't interact with each other. They don't interact with the walls. They don't interact with anything in their surroundings. And what that means, as non-interacting, is that they can essentially be thought of as gas particles or gas molecules that are floating in an infinite vacuum by themselves. They don't undergo friction when they bounce against walls. They don't undergo friction when they interact with each other. They don't see each other. And as a result, in the case of an ideal, it only depends on temperature. Temperature. And what that means then for this expression is that this term, du dV, is equal to 0. Ideal gas. And this has been shown to be true experimentally. So this means that Cp minus Cv is equal to P partial of volume with respect to temperature, a constant pressure, and using our expression, V is equal to RT over P, the state equation for an ideal gas. That means that this can now be written as P R over P, or R. P. So that comes as a consequence of the ideal nature of gas, and basically it's showing you that specifying whether you have a pressure constant or volume constant heat capacity, there is a difference. So, talking about transitions, and say transitions from state 1 to state 2, we say that a transition is reversible if after we go to state 2, we can go back to state 1. And what that means is that on our surface in phase space, so we've got our volume as a function of pressure and temperature, we're constrained to staying on this thin volume. And if we change from one surface to another, we can't come back. And kind of to foreshadow what this means is that moving surfaces means change in entropy. And it means that it's irreversible. So if you want to visualize what it means to change in entropy, as you can visualize there being an infinite number of surfaces all stacked up here. So you get this infinite stack of surfaces, and at some value of entropy, you're on one of these. And moving from one surface to the next means that the process becomes irreversible because you can't go back. And that's also kind of a point here, is that when we talk about, you may remember people talking about entropy as the arrow of time. In a closed system, entropy can only go one way. So let's say you've got a system and it's isolated, and something spontaneously happens. Well, that spontaneous occurrence means that there was a change in the entropy, and basically it means that we've changed the surface that we're moving on. And because it's a change in entropy, we can't go back. You can go back if, for example, you can open the system and you can put some work in to fix it. But in a closed system, you can't do that. And kind of the consequence of that is on day one, when I said that we think about our universe as a closed, isolated system, that means that our universe on the whole is evolving to increase entropy at all times. So this is one of those deep philosophical consequences of thermodynamics that like to be exaggerated in popular science. But from a practical perspective, it just means, excuse me, from a practical perspective, it just means that mathematically, to be reversible, you have to be on the same sheet, and changing from one surface to the next is a change in entropy. So, continuing to talk about transitions and types of transitions, we can have different types, and let's consider an adiabatic reversible process. So, in an adiabatic reversible process, there is no change in heat, which means that it really is a work-only process. Being reversible means that we stay on the same surface. And again, I say this repeatedly, but remember there's lots of types of work, even though here we're only going to talk about pressure volume work, at least for now. So returning to the first law, we have dq minus delta W is equal to du. And for being adiabatic, that's going to be 0. In our pressure volume world, this is P dV. Again, we're going to hold pressure constant, meaning that we don't have to write out a term for the change in pressure as well. And our change in internal energy can be expressed in terms of the molar heat capacities. So there's a negative sign here, so I'll put the negative there. And using our PV equals RT, we can now write negative RT over V dV is equal to CV delta T. And moving our temperatures over, or moving this over to here, we can have negative R over V dV is equal to CVT dt. And to get rid of these differentials, we will integrate from state 1 to state 2, T1, T2. Which means negative R natural log of V evaluated V1 to V2 is equal to CV natural log of T evaluated T1 to T2. And I'm going to write this out the first time. Those of you coming into grad school may or may not be comfortable working with logs. You should become so. They're quite handy. And I said I'll write it out this first time later in the class. I'm just going to skip to the answer. ln V2 minus ln V1 is equal to CV ln T2 minus ln T1 is equal to ln V1 over V2 is equal to ln T2 over T1 CV. Recognizing that that negative sign went into the exponential here, which is why it's V1 over V2 instead of V2 over V1. Whereas this one is positive, so it's 2 over 1. Oh, sorry. There has to be an R here as well. And we can take this over here to give us, and take the exponential of both sides to give us V1 over V2 R over CV is equal to T2 over T1. And then using that as an ideal gas, we have Cp minus Cv equals R Cp over C over Cv minus 1 is equal to R over Cv. And for the sake of kind of simplifying this down, we're going to call this gamma, which means that now this can be written V1 over V2 gamma minus 1 is equal to T2 over T1. And here using PV equals RT and equals 1, that lets us write V1 over V2 gamma is equal to P2 over P1, or taking these to either side, P1 V1 gamma is equal to P2 V2 gamma. And the only way that these two sets of parameters can be equal is if they're both equal to a mutual constant. So that's the consequence of adiabatic reversible work, or adiabatic reversible transitions. And now we can also talk about page 8, page 9. We can also talk about isothermal reversible transitions. And isothermal gives us dt equals 0, and because we're dealing with an ideal gas, we have du is also equal to 0, because the only time that the internal energy can change for an ideal gas is when the temperature changes. So here we have du is equal to delta Q minus delta W is equal to 0. Which means delta Q is equal to delta W, and this delta W we can write out as P dV. Putting in here, P is equal to N RT over V, and then integrating, we're going to get this expression to be the integral from volume 1 to volume 2, state 1 to state 2, N RT over V dV is equal to N RT natural log V2 over V1. And we can also here use V is equal to N RT over P. And we can draw this into our volumes. So the consequence of having an isothermal reversible transition is that Q equals W is equal to nRT natural log V2 over V1, is equal to nRT natural log P1 over P2. Okay, so now we're going to work at a numerical example for the rest of this lecture. And we're going to take the example that you have a one component ideal gas. And we're going to say that we know the initial condition or the initial state. So state 1 is V1 equals 10 liters. T1 is equal to 25 degrees C is equal to 289 K. And P1 is equal to 10 atmospheres. And then it's going to transform 1 to 2, state 1 to state 2, to some unknown volume, temperature, and a given pressure is equal to 1 atm. So this is page 11. And for this, we're going to use that the molar constant volume heat capacity is equal to 1.5 R. And as a matter of stating properties, we're going to say that this heat capacity is independent of temperature. So it's really a constant. And we're going to say find the work done, the heat absorbed, the change in internal energy, and the change in enthalpy for the following conditions. A, in the case where the transition from state 1 to state 2 is an isothermal reversible state, or isothermal reversible transition. And for 2, when it is an adiabatic reversible transition. Okay. Going to page 12. Let's start by looking at the quantity of gas in our system using the equation of state for an ideal gas. N is equal to P1 V1 over R T1, and substituting 10 atmospheres times 10 liters divided by 298 K, and then we'll put an R, which is 1 over 8.206 times 10 to the minus 2, and this has units of atmosphere, liter per K mole. So our units cancel out, leaving us mole. So we know that we've got the right expression and the right value, or the right form of the gas constant. And doing this, we get N is equal to 4.09 mole of gas. Okay, so now let's look at the isothermal process. And in the case of the isothermal process, we have that T2 is equal to T1. So that's going to set our value of T2. And then if we go and we look at the little derivation we had for isothermal reversible processes, in that case, let me find that in the notes here, we had, here it is, right, we had this isothermal reversible transition, and we had this as the final consequence. So this is equal to this, and if you look, nRT cancels, the natural log, so we can take the exponential on both sides, and that means that we have V2 over V1 is equal to P1 over P2, and that can be rearranged to P2 V2 equals P1 V1. And because we have V1, P1, and we have P2, and we also know T2, we can now find V2. V2 is equal to P1 V1 over P2 is equal to 10 atmosphere times 10 liters over 1 atmosphere is equal to 100 liters E2. So we found the temperature and the volume of our system, and from that we want to get the work done and the heat absorbed, and they're the same, right? Because we have Q is equal to W is equal to N R T ln P1 over P2 is equal to N R T ln V2 over V1. Right? So if you want to, you can put in 10 and 1, or you can put in 110, but it's the same problem, right? Because nRT is the same on both sides, and ultimately we get 4.09 mole times 298 K times 8.314 joule per K mole. So our units here cancel out, giving us just joule times natural log of 10, or Q equals W equals 2.33 times 10 to the 4th joule. So that gives us the work and the heat absorbed. But we have an ideal gas, which means that the change in the internal energy is only due to the change in the temperature, which we said is 0 in this problem because it's isothermal. Therefore, du is equal to 0. Okay, now we can go to the enthalpy. And there's several ways you can get at that. One way is to say that dH is equal to Cp dt. And then we're going to integrate this from H1 to H2, from T1 to T2. And to get the constant pressure heat capacity, we have C molar constant volume heat capacity is equal to 3/2 R, which means the constant volume heat capacity is N C molar is equal to N 3/2 R, and we have Cp minus Cv is equal to R. And we can put all that together to get Cp is equal to Nr plus N Cv is equal to Nr plus N 3/2 R, which goes into the integral, giving us delta H is equal to the integral T1 to T2 Nr plus N 3/2 R dt. There's no T in there, which means that this is equal to constant T evaluated, T1, T2 is equal to 0. So delta H is equal to 0. The way that you could get at this in terms of work, if you wanted to, is you could say that delta H is equal to delta U plus delta PV is equal to, and again, that's 0. Which then we could say is equal to P2 V2 minus P1 V1 is equal to 1 times 100 minus 10 times 10 is equal to 0. Or if you want to do this entire thing symbolically, you could say, you could use PV equals RT, and we could write that delta H is equal to NR T2 minus T1. Again, this is equal to 0 because it's isothermal, so delta H is equal to 0. So it's nice that you can go about getting the answer in many different ways and get the same answer. Okay. And then the next question was do the same, but now for an adiabatic reversible transformation. So going back to our notes, we looked at adiabatic reversible transformations, and what came out of that was that this expression has to be equal to a constant. So these two are equal to each other. So P2V2 gamma is equal to P1V1 gamma. Because P1 and V1 are known and P2 is known, now V2 is equal to P1 V1 gamma over P2 to the 1 over gamma, which is 100 atmospheres times 10 liters to the gamma over 1 atmosphere raised to the 1 over gamma. Gamma is equal to Cp over Cv is equal to R over Cv plus 1 is equal to 2/3 plus 1 is equal to 5/3. So that gives us V2 is equal to 39.8 liters. So now we have pressure, temperature, and volume in state 2. Or I guess we have pressure, volume, and then the temperature comes from P2 V2 over NR is equal to T2 is equal to 1 ATM times 39.8 liters over 4.09 mole times 8.2 times 10 to the minus 2 liter atmosphere per mole K. T2 is equal to 119 K. Going to the question of energy. Let's move this around. Going to the question of energy. Delta U is equal to the integral U1 U2 du is equal to the integral T1 T2 the molar entropy dt, and recognizing this has units of joule per K per mole, and this has just units of joule. That means we have to have an N in there as well. Delta U is equal to 3/2 R119 minus 298 times 4.09. So this is in K, this is in mole, this is in joule, which means that this must be 8.314 joule per K mole in order to get K and mole to cancel out, just leaving joules, or du is equal to minus 9.1 times 10 to the third joule. And then, by definition, delta H is equal to delta U minus delta PV is equal to delta U minus nRT2 minus nRT1 using PV equals nRT, or delta H is equal to minus 9.13 times 10 to the 3 joule minus 4.09 mole times 8.314 joule per K mole times 119 minus 298 K, or delta H is equal to minus 3043 joule. That's page 16. Okay, so that's the first part of this example. The second part of this example is a follow-up in which we say that if we know the initial and the final state, show that by taking different transformation paths, we get the same state. And we're going to use the energy as an expression for the state function. And basically, our first state is going to be V1, T1, P1 is equal to 10 liter, 298 K, and 10 atmosphere. And we're going to have this transition to state 2, which is 39.8 liter, 119 K, and 1 atmosphere, which was the output of that adiabatic calculation. And the problem asked us to look at 5 different paths. So let's start with the path which is isothermal, followed by constant volume. Constant volume. Which means that basically this is going to an intermediate, and from that intermediate it's going to the final. So to say that it starts out isothermal is to say that the intermediate temperature is the same, and then to say that the following step is constant volume, that means that the volume in this step must be the same as here. Which means P we can find from P equals nRT over V, if needed, because we know Vt and N for this intermediate state. So the state function energy is additive, so we can do a delta U1 and a delta U2, and then say delta U is equal to delta U1 plus delta U2. This first part is isothermal, meaning delta T equals 0. And it's an ideal gas, and because delta T equals 0 and U only depends on the change in temperature, that means delta U1 is equal to 0. Now coming over to this problem, in this side, we're going to have delta U2 is equal to the molar constant volume heat capacity, delta T N, right? Because we're doing a constant volume process. And we know this, and we know this. So delta U2 is equal to 3/2 times 8.314 times 119 minus 298 times 4.09, or minus 9.1 times 10 to the 3 joule. So delta U equals minus 9.1 times 10 to the 3 joule. And that's the first path we're going to follow. The next, out of focus there. The next path is constant volume followed by isothermal. Okay, so again, V1, T1, P1 are known. 10 atm 298 K and 10 liters. V2 is equal to 39.8 liters. T2 is equal to 119 K, and P2 is equal to 1 atmosphere. Constant volume means that V prime is 10 liters. Isothermal means that the temperature is 119, which leaves P prime as coming from nRT prime over V prime. So we can substitute in to get pressure if needed. Okay, the constant volume change in energy is just what we solved before, right? Which was delta U1 is equal to 3/2 R times delta T. And isothermal, therefore delta U2 equals 0. So delta U is equal to minus 9.1 times 10 to the 3 joule. So that wasn't very exciting, was it? But that's okay. Oops. Oh. So the next path is isothermal, followed by constant pressure. So V1, 10 liter, T1 is equal to 298 K, P1 is equal to 10 ATM, V2 is equal to 39.8 liters, T2 is equal to 119 K, P2 is equal to 1 ATM. Isothermal means that T prime is equal to 298 K. Constant pressure means that P prime is equal to 1 ATM, which means V prime is equal to nRT prime over P prime. Isothermal, delta T equals 0, therefore delta U equals 0, or delta U1 equals 0. Constant pressure, well, constant pressure is delta U2 is equal to the constant pressure molar heat capacity, delta T N minus P delta V. I'll write this out. The constant pressure molar heat capacity is equal to R plus CV is equal to 5/3 R, or sorry, 5/2 R. I can't read my own notes. 5/2 R. And then for that delta V, that's P2V2 minus P2V prime. And what we can do here is we can also substitute in V equals nRT over P. So that becomes delta U2 is equal to 5/2 R N delta T for the first term, and for the second term it's going to be minus N R delta T. Because we substituted in nRT over P in for the volume, and then the pressure is canceled for each one of those, giving us this expression. So delta U2 is equal to, if you want to pull things out, well, just substitute in R delta T 5/2 minus 1. That's 3/2. So delta U is equal to 4.09 mole times 8.314 joule per mole per Kelvin times delta T, which is from here 119 minus 298 times 3/2. And you've seen this before, the last 2 pages of notes, right? So delta U is equal to minus 9.1 times 10 to the 3 joule. So far, all 3 paths have wound up with the same value for the energy. Okay, next path, constant volume, then constant pressure. So V1 equals 10 liters, T1 equals 298 K, P1 equals 10 atm, going to V2 is equal to 39.8 liters, T2 is equal to 119 K, P2 equals 1 atm. Constant volume means that V prime is equal to 10 liters. Constant pressure means P prime is equal to 1 atm, which means T prime, PV equals nRT, is equal to P prime V prime over nR. And when you substitute in 1 atmosphere, 10 liters, and 8.2 times 10 to the minus 2, you wind up, 4.09 and 8.2 times 10 to the minus 2 atmosphere liter per mole K, you wind up with 29.8 K as T prime. So coming over here to the left, delta U1 is equal to the molar heat constant volume heat capacity times delta T N, which is equal to 3/2 R delta T N. Coming over here, we get delta U2 is equal to the molar constant pressure heat capacity delta T N minus P delta V. So that we know is 5/2 R And that delta V, we're going to write out again as NR delta T, and we have delta T here, which means that delta U2 is equal to NR delta T 5/2 minus 1. Let's call this delta T2 and this delta T1 because that temperature to that temperature and that temperature to that temperature are two different delta T's. And that means now that delta U is equal to 3/2 R delta T1 N plus N R delta T2 times 3/2. That's so substituting delta U is equal to 3/2 times 8.314 times 4.09 so I got rid of that, and that times delta T1, which is 298.29.8 minus 298 plus 119 minus 29.8. So delta T gives us delta U is equal to negative 9.1 times 10 to the 3 joule. Okay. And last but not least, we will take two pencils here. Constant pressure then constant volume. V1 is equal to 10 liters. T1 is equal to 298 K. P1 is equal to 10 atmosphere. V2 is equal to 39.8 liters. T2 is equal to 119 K. P2 is equal to 1 atm. Constant pressure means that P prime is equal to 10 atmosphere. Constant volume means that volume is equal to 39.8 liters. T prime is equal to P prime V prime over NR, substituting in P prime V prime 4.09 for the number of moles and 8.2 times 10 to the minus 2 atmosphere liter per mole Kelvin. We wind up with T prime is equal to 1187 K. Okay, so this path, delta U1 is equal to constant pressure, molar heat capacity, delta T N minus P delta V. That's 5/2 R. For delta V, we substitute NR delta t, which means delta U1 is equal to nr delta t 1 times 5 halves minus 1. For this side of the equation, delta U2 is equal to constant volume molar heat capacity times delta T2 N. That heat capacity term is 3 halves R, which means that delta U is equal to N R 3 halves, because that's 3 halves, times delta T1 plus delta T2 in R. So delta U is equal to 4.09 times 8.314 times 3 halves times 1187 minus 298 plus 119 minus 1187, or delta U is equal to negative 9.1 times 10 to the 3 joule. And that is all we're going to work through. But you can see kind of the general patterns of what we're doing, and you can also kind of see the kind of cadence you get when you're working in these problems. If you know the initial and the final state, and you know the path, you can figure out what goes into these intermediate state variables. So with that, prepare for the quiz using these examples, and I will see you on Monday.